Hey guys, time for another installment of Physics in the Flesh, the Millikan oil drop experiment 1. This is such a famous experiment that it has been duplicated multiple times in laboratories all across the world. It's also been done for undergraduate students when they pursue their bachelor's degree. Very popular, very meaningful experiment. That's why it's used in these problems as well. Consider two parallel plates 1.90 millimeters apart with a potential difference of 220 volts and a positively charged upper plate. A charged oil droplet with a mass of 5.89 times 10 to the minus 10 kilograms is suspended between the plates. Determine the sign and magnitude of the electric charge on the oil droplet and calculate the electron deficiency or excess. So I'm going to draw a picture first of all because I haven't been given one in this problem. Sometimes with these types of problems you're given one, sometimes you aren't. So we've got two parallel plates, and I know that the top one is the positive one. So I'm going to draw two parallel plates, and obviously based on the second piece of information, they're horizontally placed. So the top one is positively charged, and the bottom one is negatively charged. Now I've got an oil drop in the middle, and it says it's suspended in between. So it's just hanging there. Now, because this isn't a charge, it's an oil droplet, we can take gravity into consideration, the weight. Think about this. The mass of an electron is on the order of 10 to the minus 31. That is extremely tiny. That is 21 orders of magnitude smaller than the mass of this oil droplet. So even though we ignore the mass of the electron, we are not going to ignore the mass of the oil droplet. Okay, so we know that it has a force of gravity going down. But here's the catch. If it's suspended, that means it's not moving. In other words, there has to be another force counteracting this in the opposite direction, which means the electric force has to be going up. If the electric force was going down, of course, the particle would go down, but there has to be something opposing it. So electric force is going up. Now, if the electric force is going up, now by that argument, that means whatever charge this is attracted to a positively charged plate. Therefore, the oil droplet must be negatively charged. So that's how you figure that out. Okay? All right. So we have our setup. I'm going to go ahead and define my positive direction to be up. So this will be my positive y direction. And I need to find the sign and magnitude of the electric charge. So I'm going to go ahead and use the fact that, you know what? The oil drop is suspended, which means that charge isn't going anywhere. That means the net force in the y direction is 0. And in my y direction, I've got my electric force. I've got my force of gravity. Now notice that I'm adding them together, and the reason for that is I still have the vector symbols on top, so I haven't taken the direction into account yet. But once I drop those symbols, I have to assign a direction. Now according to what I've defined here, force of gravity is going down, it's in the negative direction. So I drop the symbol, Fe stays positive, Fg becomes negative. Fe minus Fg equals 0. Now I'm going to go ahead and take Fg to the right side to simplify this. Fe equals Fg. And I know that the electric force is given by the charge times the electric field epsilon. Fg is just mg. Now the nice thing is when you're working with parallel plates, because there is a potential difference between the plates delta V, right? And there's also a separation distance between the plates delta D. The electric field between two parallel plates can actually be rewritten as delta V over delta D. And that is what is a game changer in this problem. Okay, so now solving for Q, multiply both sides by delta D, divide both sides by delta V. Q equals mg delta D over delta V. Okay, so that's how we end up with that expression. And at this point, you just got to plug in your values. So here I go. Okay, so Q equals, now the mass is given 5.89 times 10 to the minus 10 kilograms. So it's just up there. 5.89 times 10 to the minus 10 kilograms. G is my acceleration due to gravity, 9.8 newtons per coulomb. Delta D is the separation between the plates. In the question, I'm told that they are 1.90 millimeters apart. So remember, in these formulas, we have to put SI units. So we have to put meters. So to go from millimeters to meters, I have to divide by 1,000 or multiply by 10 to the minus 3. Okay? divided by delta V, and I'm told that's 220 volts. Okay, there we go. So I have to punch this into my calculator, and when I do, I end up with Q as 4.99 times 10 to the minus 14 coulombs. Now, I did write Q here because that's how it came out when I plugged it in, but bear in mind that I stated up here it's negatively charged. So therefore, I'm going to put my actual answer as minus 4.99 times 10 to the minus 14 coulombs. There we go. So there's my charge. Now, the last part of this question is to determine whether or not I have an electron deficiency or excess. And what that means is, well, we know that all everyday objects are made up of billions and billions of particles, electrons and protons, but most of the time, the amount of protons and electrons cancel each other out, which is why objects are neutral. If I touch, for example, this piece of paper, it's neutral. I don't get shocked. There's an equal amount of protons and electrons, you know, roughly. And even if there is an excess, it's so small I don't feel the charge. In this case, my object isn't neutral. It has an excess charge. And that excess charge is minus 4.99 times 10 to the minus 14 coulombs. So if I want to figure out how many electrons there are, well, first of all, look at this. Electrons are negatively charged. So if I have a huge negative charge, that means I have an excess of electrons. Okay? That means I have too many electrons because I have too much negative charge. I have a net negative charge. Now, if I want to find out the electron deficiency or excess, that means I'm trying to figure out the number of electrons. And the number of electrons is just going to be, well, whatever total charge you have divided by the charge on one electron, right? It's just a logical formula. So I'm just going to go ahead and do that. Okay, so Q is minus 4.99 times 10 to the minus 14 coulombs. That's my total excess, divided by the charge of one electron, minus 1.602 times 10 to the minus 19 coulombs. Remember, when you have a negative exponent and the number gets bigger, that means the overall number is getting smaller. So when you calculate this out, you're going to end up with an n value of 3.1 times 10 to the 5 electrons. And that is excess. And that's it for this video, guys. I hope you enjoyed it. If you have any questions, be sure to leave them in the comments section below. Otherwise, I look forward to seeing you guys tomorrow for video 167, another version of today's video, actually. The Millikan oil drop experiment 2. Different problem, a slightly different scenario, but similar type of strategy. So stay tuned for that. See you tomorrow, guys. Alright guys, that's it for this video. I hope you enjoyed it. If you did, be sure to smash that like button so I know what I'm doing makes sense to you guys. And you know how you can stay tuned for my latest videos? By subscribing to Physics in the Flesh. I post every weekday at 12 noon, and this way you guys can always be the first to know when I post a new video. As always, guys, thank you so much for watching. If you missed any of my earlier videos, be sure to click over there on the right. You can click and watch those videos on your screen right now. Anyways, guys, Physics in the Flesh out. Woo-hoo! Holy crap, my nose looks big on camera. I gotta find a new angle.